Go to question 31. Question 31 says, if the neutron's quark makeup was an up quark, a bottom quark, and a top quark, what property of the neutron would it now conserve? So, of all those properties of the neutron that we know of, charge, baryon number, strangeness, all of those, what properties would it still retain? Okay, so would it still retain the same charge? Would it still retain the same baryon number, strangeness, both A and B, none of the above? Well, in order to do this, again, you have to basically know the baryon number, the charge, the strangeness of all of these, right? So if it was UBT, here's the symbol for the neutron, the charge of this is 2/3. The charge of the bottom quark is -1/3. The charge of the top quark, right? Top quark, the charge is +2/3, right? +2/3. Up is +2/3. The bottom is at -1/3. The top is +2/3. So what would that be here? 2/3 -1/3, 1/3 plus 2/3 plus 1. So the charge of the neutron would be +1. Well, we now know the charge of the neutron is 0, so it would not retain the same property of charge. So this is not the answer. Baryon number, well, up quark is a baryon number 1/3, baryon number 1/3, baryon number 1/3. All the quarks have the same baryon number of 1/3, so it will conserve the property of baryon number. Okay, strangeness, none of them is the strange quark. Only the strange quark has a strange property of -1. So the strangeness of all of these is 0. Well, we know the strangeness property of the neutron is 0, right? So it would also retain the same property of strangeness. So the only one that would change is the charge. So the answer is D. D. It would retain the property of baryon number and strangeness. Okay. We could also add one other property here. We could say, we could make this none of the above, A, B, C, D, E, F, none of the above, and we would have another choice, E. How about the mass? How about the mass of the, or we could say the energy of the neutron? Would it retain the same property? Well, as it turns out, every quark has a certain energy, okay? So let's give those energies. These are called rest energies. From Einstein's theory of relativity, E0 is equal to m0 c squared. So if I want to say the mass of a quark, I can also state the energy of the quark, okay? So the energy of each quark, up, down, charge, strange, top, bottom. The energy of the up quark is 360 mega electron volts. Okay, mega electron volts. The energy of the down quark is 360 mega electron volts. These are rounded. They're not very, very exact. Okay. The energy of the charm quark is 1,500 mega electron volts. The energy of the strange quark, 540 mega electron volts. The energy of the top quark, 173 giga electron volts. And this also goes to show you why we discovered the charm and strange and top and bottom quarks much later after we discovered the up and down quark. Okay, so we discovered evidence for these quarks much later because they are only discoverable at much higher energy. So these are mega electron volts, million, and whereas the top and bottom quark are giga electron volts, which is a billion. Okay, so the bottom quark is 5 giga electron volts. So the top quark is the most energetic, 173 giga electron volts. Okay, so what would it do? Now, if it was made up of up, bottom, top, what would its energy be? Well, that's going to be 360. Bottom is going to be 5 giga electron volts. This is mega electron volts. And then the top would be 173 giga electron volts. So what would its total energy be? Well, in giga electron volts, 360, if you change that to giga, that we would have to go back, that would be 0.36 giga electron volts. So its total energy would be 178, when you add 5 to 173, 178.36 giga electron volts. So now the neutron would be a very, very energetic particle. 178.36 giga electron volt energy, rest energy. What is the energy of the neutron now? It's up, down, down. That's what the neutron is made up of. So it's 360, 360, 360, 360, 360, 360. So it's 0, 18, 1, 4, 7, 10, 1080 mega electron volts. Okay, so the rest energy of the neutron is approximately the same as the rest energy of the proton at 1080 mega electron volts. How many giga electron volts is that? 1.08 giga electron volt, if I change it. So the rest energy of the neutron would greatly increase from 1 to 178 if the quark makeup had been changed. So definitely this property of mass or energy would not be retained. Only baryon and strangeness number would be retained. Okay? Thank you.